Hello, good day. My name is Victor Chaves from the University of Seville in Spain. I'm going to present the work calculation of fatigue limits in notches with a micromechanical model in a simple way. Well, let's begin with the introduction. I'm going to talk about fatigue limits in notch components, which is a problem of the mechanical industry for a long time. We have had many proposals in the last decades to make predictions of the fatigue limits as the classical critical volume methods of Peterson or Neuber. They are based on the calculation of the fatigue notch factor, KF, and for the calculation they need the elastic stress concentration factor, the notch root radius, and the material constant. They have advantages, this classical method. They are quite precise, quite accurate, and handy for engineers, mainly that. So they have been in use for years and years. They have as well disadvantages. Okay, the material constant is only known for steels and aluminium, so you cannot use it for titaniums. Then if you have a complex geometry, you don't know how to define the KTs. Where is which is the nominal stress, which is the stress if you have complex loading as well. It's not easy to define. And finally, you don't have the crack growing in the material, which is the real physics of fatigue. So later, some authors proposed models based on linear elastic fracture mechanics. This is a great advance. It's work. So we have Murakami, Lucas, Smith and Miller, etc. More recently, Professor Taylor proposed the theory of critical distance, which is a critical volume method, but more advanced than the classicals. Basically, the material constant is calculated through fracture mechanics. So it's a huge advance because you can use it for any material and in a simple way. And you can use it for complicated geometries because you don't have KT anymore. And so it gives good predictions and it's handy for engineers. So it's quite good. The disadvantage I find is that it doesn't include the crack growing in the material. So nowadays we know that we talk about fatigue limits. The crack spends most of its time during the initiation, during the first period of growth, in the short crack period, not in the long crack period. So for fatigue limits, should be better to use the short crack mechanics instead of long crack mechanics. That's why during the 80s, in the last century, some researchers work in this short crack mechanics and included Navarro and de los Rios that develop a theory of short crack growth, which is nowadays called NR model. According to this model, the crack is stopped at the microstructural barriers of the material, let's say the grain boundaries. So the crack stops at the barrier. If the stress, applied stress is high enough, the crack will pass the barrier, grow along the material, stop at the next barrier. If the applied stress is high enough, the crack will pass. If not, you have a non-propagating crack. And in this model, the strength of the barriers are adjusted with the Kitagawa-Takahashi diagram of the material, which it includes the short crack period and obviously the long crack period. The advantages of this model, for me, it captures the physics of the fatigue process, that is a short crack growing in the material, and it has shown to give good predictions. Disadvantages, the equations are different for each notch geometry and it has to be solved numerically. It's not simple, so it's not handy for engineers. So which is the objective of this work? To give a simplified version of this model so it can be used by engineers. So let's describe briefly the model. In 4 tips. It's assumed that due to the cyclic stress, the crack is initiated in the most favorable grain. The crack and its subplastic zones at the tips grow due to the cycle loading until reaching the first microstructure barrier, the grain boundary. If the stress is high enough, the crack will pass this grain boundary and continue through the second grain. And this process is repeated until failure or until having non-propagating crack. Mathematically, the crack and the barriers are modeled by a continuous distribution of dislocations. So the crack will pass the barrier, the ith barrier, if the local stress at the barrier, sigma 3, is higher than the barrier strength, sigma 3 asterisk. So if sigma 3 is bigger than sigma 3 asterisk, the crack grows. If not, the crack stops. The barrier strengths, as we said before, are deduced from the Kitagawa-Takahashi diagram of the material, and the barrier stresses, sigma 3, are calculated from the equilibrium of dislocation at the crack line. And this equilibrium is obviously affected by the geometry and the loads. For the simplest case, that is the mode 1 crack in an infinite plate subject to a cyclic uniform tensile stress, we have a Cauchy type integral equation, which is shown, and it has an analytical solution with the Muscaliishvili theorem. So for this case, the situation is easy. But the crack grows from a notch. The integral equation has no analytical solution, and it has to be solved numerically. Besides, the kernel of this integral equation is only known for a few simple geometries, circular holes, semi-infinite plates, but not, for example, for a V-notch. So in summary, the NR model for fatigue at notches is not simple. Let's see now the simplified version of the model we are going to see, and is focused on these two main difficulties. So two simplifications are made. First of all, the elastic field created by a dislocation in the vicinity of the notch is simplified to that of a dislocation in an infinite medium. In this case, we have an analytical solution, and we have studied this simplification, and it works well. Why? Because the elastic field created by a dislocation is based mainly on the distance between the point to the point you want to study another dislocation, and in a second level to the boundary condition, the presence of the notch. The second simplification, we have the elastic stress gradient at the crack line created by the notch. We simplify it to a uniform stress, no gradient, and this uniform stress has the value of the midpoint of the crack line. So this is a huge simplification for us, because now we have again a simple analytical solution and a numerical. Let's see if it works or not, because simplification is huge. So we have examples here of fatigue limits for circular holes as function of radius. We see some experimental results, and we see the predictions with the classical NR model and with this simplified version. And we see the two curves are very similar. So despite the big simplifications, the results are very similar. So which would be then the summary of the procedure? I'm going to explain it. On the left is the procedure, and on the right an example. So the first thing is to make a linear elastic analysis of the solid and to find the point of maximum stress and to define the crack line normal to the notch contour at this point. We are going to do it, the example, in a circular hole of radius 0.5 millimeters in an infinite plate of a steel. We have the analytical solution of the for the elastic field. Second is calculate the stress normal to the crack line, sigma y, at the midpoint of the successive cracks. The cracks we have first in the first grain, then we will go to 3 grains, 5 grains, etc. So we calculated at this case, because the grain has 80 microns, so at 20 microns, 60 microns, 100 microns, and the stress in the point will be 2.74, 2.35, always obviously a bit less always than 3, which is the KT. Then we calculate the values of the Kitagawa-Takahashi diagram at this crack lengths. We do it with an equation proposed by Vallellano, and you see the values on the right. We divide these values, and these are the stresses you need to overcome the barriers. So dividing these two values, we get the successive values. We see the number for the first grain 115, for the second grain 126, for the third grain 129, for grain 128, and we finally locate the maximum value, first local maximum value of this list, which is the number 3, 129.4, and this is the notch fatigue limit, and at the same time will be the maximum length of the non-propagating crack. So this third barrier is this important one. We have compared with some experimental results the fatigue limit predictions with the model and results from the literature. We see in the graph, we show the errors, and we see the error bands of 20%. We have done it only for circular holes in plates and bars. We have 59 error results, and we see that the errors are mostly inside the bands of 20%, which are supposed to be acceptable results in fatigue limits. What is more important is that most of the results out of these bands are in the conservative part, in the lower part, and not in the non-conservative. So at least when you have bigger errors, they are conservative, which is good for engineers. The summary of the results, and I have included the point method predictions as well. So three statistical values we have analyzed. The average error, which is for the simplified NR model, is 12.5%, while point method is a bit better, 11.5% of error, the average of all the result. But if we see which is the percentage between the two bands of 20%, the result with simplified NR models are better. 81.4 are inside these bands, while with the point method is it's good, the result as well, 24.6. And if we want to see which are the results we have an error less than plus 20%, which means that are acceptable or conservative predictions, with the simplified NR model, the 100% are inside this or over this band. This is very important because the results from this model are, let's say, acceptable or conservative in all the cases. So conclusions. The simplified version of the NR model gives very similar results as compared to the exact version of the NR model. It's easy to use, and still the basic physics of the NR model are maintained. It can be applied to any notch geometry and material. It provides acceptable predictions, or at least conservative, which is very important for engineers. So I think it can be a useful tool for researchers and engineers in the field of fatigue, as it combines both physics and simplicity. Thank you very much for your attention.